All right. Good morning, everyone. Today, we will start talking about markers that aren't working. Let's try this. Oh, also pretty bad. We're off to a great start here. All right, hang on. We'll use mine. So we are going to be talking about going beyond linear models. So gain in predictive power and flexibility in fitting models. But we lose interpretability. So last time we talked about the use of instrumental variables, right, as a way of determining real relationships between our explanatory variables and our response variables. So that's kind of one school or approach in thinking about data analysis, is specifically focusing on understanding that relationship. The other side of the coin is really focusing on prediction. So as we move more and more towards here, you start to care less and less about these, betas, right? The relationship, the direct relationship between your explanatories and your response, and you mainly care about being able to get really good measures of your y-hat, essentially, getting your predictions to be as close to your observations as possible. So we're going to go step by step through a bunch of functions, or a bunch of different types of regressions. We're going to look at polynomial, step functions, regression splines, smoothing splines, and general additive models. Okay. So polynomial regression. So we actually looked at an example of this in a previous lecture where I applied a bunch of polynomial terms to our explanatory variable. So this might look something like a transformation from this plus beta 1 x I plus epsilon I to something like this, yi equals beta 0 plus beta 1 xi plus beta 2 xi squared plus beta 3 xi cubed, and so on and so forth until you get beta n xi n. So the way you should think about this is, as I add more and more parameters into the model, it increases the sort of flexibility of fitting some kind of trend pattern to, all of these betas to let me get closer and closer to y. However, this can be overly flexible. And take on strange shapes near boundaries. Of x. Okay, so if I start to have something curvy, in a linear regression, I would only really able to fit some line like this. But with a polynomial regression, I might be able to start to fit some more sort of curvy lines to get essentially sort of closer to my observations. Okay. There's a different way I can try and fit this. So let me redraw that plot really quick. Instead of trying to create some kind of polynomial term, an alternate method that I could take is to separate this out into several linear regressions. Okay, so I could draw a line here, a line here, a line here, and a line here. Okay. So this type of approach is known as a piecewise or segmented regression. And so if you start something like this, then you could divide this up into multiple pieces. So we take our original regression, y equals beta 0 plus beta 1 times x, and we split this up Same thing here, but this only applies for x's that are less than BP, which stands for a breakpoint. I'll just write that here, breakpoint. And then you have a separate linear regression, yi equals beta 2 plus beta 3 times xi for all x's greater than your BP. So right here, I've selected several breakpoints, right? So that might look something like this. So this is an application of hopefully something that's pretty straightforward for you guys now, except we're just dividing our data into these multiple sort of sections. If you think about it, you could add many, many, many breakpoints, right? And if you were to do that, that's how, in fact, you could add a breakpoint for every single point. And that's how you would end up with something that looks like this, right? So something that would connect every single data point. Yeah, so two things to think about regarding breakpoints, okay? You need to think about, one, how many breakpoints you should have, and then two, where the breakpoint should be located. What do you guys think? What is one possible way to think to come up with a breakpoint or multiple breakpoints? So you mean if you chose multiple breakpoints, seeing if it goes up and down? But what if it were like, what if it was like this? Right, then maybe you would want one here. So it's not necessarily about the slope changing. And the thing is, you might not be able to visualize that to decide your breakpoints, right? Because this is just in a sort of 1 or 2-dimensional thing, but you might have more dimensions. Yeah.
Significant intervals on the x-axis.
Yeah. But what if all of the action were happening in a small space? So like, what if so for example, what if you had something where you wanted to like do that, right, in a small area? Yeah.
What if you drew lines between every two points that are neighbors in the x-axis, and you grouped them until you found the number of lines that had the that covered most amount of points with the same slope? I don't think I'm explaining this particularly well, but you sort of like grouped it until you had points that fit slopes. But I don't.
Yeah, I think you might be on the right track here. Okay, let me give a little bit of a hint here. Let's see. Let's suppose that I decided to add a breakpoint for every pair of points here. So literally every point has a breakpoint, and I draw a regression line in between. So there's a straight line in between every 2 points. So we've done stuff kind of like this before. So what's the issue here? Overfitting. Okay, how did we deal with overfitting before? What was that? Yes, so that is, yeah, one way you can do it. AIC or BIC. But in just this case, more generally, right, you can do a cross-validation, okay? And if you do out of sample, if I take out 1 or 2 points here, this is probably going to do really poorly to predict those, okay? So in the same way that we have been using out of sample cross-validation to sort of avoid overfitting and do like model selection and that sort of thing, this is just another adjustable parameter, right? BPs. So I can run piecewise regressions through cross-validation and with different combinations of breaking points at different locations in order to figure out which BP, which set of BPs would provide you with the best out of sample prediction. Okay. So basically the idea is, okay, I test these BPs like this, and then I do another set of BPs, right? I can look at a bunch of different combinations of them until I figure out which breakpoints give me the best out of sample prediction. Okay, any questions about this? So you don't need to worry too much about this in practice. We're kind of stepping through the evolution of regression approaches to get at things that are slightly more commonly used, but we need this as a sort of buildup. So what happens? Okay, I just erased it, but we had polynomial regression here, piecewise regression. What about if we combine those? So the combination of these guys are known as splines. So this is a piecewise polynomial function. But there are some hidden details, okay? So let's take a look here. X and Y. So this is a piecewise cubic, which is 2 cubic or polynomial regression line segments. So one of the things that I'll say about this is that with splines, when you combine piecewise and polynomial, you have many, many degrees of freedom, right? You have a lot of flexibility because I could be adding lots of polynomial terms or I could be adding lots of breakpoints. Generally, there's enough flexibility in these sort of 2 dimensions that most of these things don't go beyond cubic polynomials because there's enough built-in flexibility that once you do the cubic and the piecewise, you can build any line that you could possibly want, okay? So one of the things you'll note in particular right here is that the way I drew this, there is like a discontinuity between my first and second line segments. Okay, there's no reason why these 2 lines have to meet at the sort of breakpoint, or there's no sort of mathematical reason why in here. And that's the same for our piecewise and segmented regression. Okay, they don't have to touch. But you can actually build that in. So plus an additional constraint that the lines must touch. Okay, so that's going to look something like this. And here, you'll notice, okay, now you've added some kind of constraint that basically enforces these guys to be the same at that breakpoint. But you'll also notice that it's like a very sudden, it's not a sort of smooth meeting of the lines. So the last thing, so this is known as a continuous piecewise cubic. And the last one is that you add another constraint that lines must be smooth. Oops. Which means the first plus second derivatives are continuous at cutoff point. And this is what we call a cubic spline. Okay, it is essentially a piecewise cubic with these two constraints. And that's going to make our line look smoother. So that might look something like that. And this is known as a knot. Okay, so when you include, so the breakpoint where you have these constraints where they touch and have to be smooth, that's known as a knot. So the way this works is we transform this data like so. So here, the x's are transformed by what's known as a basis function. And this basis function is the transformation into a cubic function with these constraints. Okay, so we're not going to get into the theoretical sort of mathematical formulation for this. It doesn't matter too much because these betas that are getting generated are not really something that you can interpret, right? Because it applies to some kind of weird transformation of your x's. And the k's are the number of knots. You have to have a couple extra one of these to accommodate the constraints associated with the knots. So as I was mentioning, so the cubic splines are the most common. We trade off the polynomial, as I was just mentioning. So this is like having lots of xn terms for knots. So these knots are the thing that allow us to add sort of flexibility. Okay, so let me draw a couple points here. Okay, I'm just going to copy that. And the whole idea here is as I add knots, it allows me to sort of warp my fit to be sort of more and more flexible to the points. Okay. So how do I choose the number of knots? So if I add more and more knots, my lines get sort of more squigglier and squigglier, right? So that would be an example of overfitting. Yeah. And how do we deal with overfitting? Cross-validation. Yes. Okay. So this is going to be like the punchline of every question I ask you guys. Okay. As I was saying, cross-validation is going to be really important and applied to lots of these things. So I can use cross-validation to determine sort of how many knots and their respective locations. So let's go ahead and take a look at this in a more applied setting. Okay. So we're going to do something similar to what we've done in the past in essentially creating an artificial data set to run our regression on. Okay. So hopefully this will be somewhat familiar to you guys, but it's going to be slightly modified this time. We're going to have 1,000 x's between 0 and 5. We'll have some error. And then we'll have a y. And our y, oops, is going to be slightly different. It's going to be sine of x plus cosine of 10 times x plus 0.5 times x plus a deviation. Or sorry, plus our error, not deviation. All right, so we run those. And I'm going to go ahead and start showing some examples of these models. And the first thing we're going to compare against is our linear model. And then we're going to compare this against a polynomial model. And I'm just going to have 25 terms in my polynomial model. So it's actually pretty straightforward how to do this. I can have this term poly, which will build out my x's into this sort of table where I have x, x squared, x cubed, all the way up to x25. And I actually want to plot this, so I'm going to do a prediction. Across the range of my x's. Okay, so let's look at what this looks like. So this set of y's that we generated up on line 4 is going to have these values, and when we plot it against x, it'll look something like this. So we've got some kind of sinusoidal wave pattern. So you can see we're fitting something fairly complex now. So let's include the actual and compare it against the linear. So I'm going to add 2 curves to it. Whoa, hang on. One second. What did I do here? Oh, yes. That's actually what I meant to do. Okay, so let me rerun everything. I was like, the line looks different than it did in the past. Okay, here we go. That's what I wanted. We can see in the sinusoidal wave, these are like getting kind of bigger and smaller. Okay, and then we have kind of a clear linear trend line to go through all of these things. Okay. And you guys can probably imagine, right, the interpretability of creating a line that kind of fits this is not as obvious anymore. If you were to create a more sort of squiggly line. But this is what we have right now. And let me just pull it out to make it a little bit bigger. Yeah. So we can see the actual function, the one that we know is true in blue. And then the red line represents how we would approach this with a sort of simple linear regression. So now let's take a look at how to do this with the polynomial, or to plot the polynomial, since we've done that already. And actually, one thing that I'll quickly say is that if I plot the residuals, before we get there, this is the residuals, okay? Does that look problematic to you guys? Right, how do we want our residuals to look? Yeah, sort of really random across the uniform range of our fitted y values. So this is no good. And so we need better ways to approach this. The blue line was the model. So, okay, you're talking about here. So there is a blue line right here. So this blue line represents what we know is the true model. Okay, the true relationship between X and Y. So I'm gonna copy and paste this bit here. And I'm gonna add the other line against my prediction. And we'll see what 25 polynomials do for us. Okay, not too bad. So what we see here is that the waves generally kind of line up, okay? And the amplitude of the waves are similar. So the largest one is here, and then it gets kind of smaller. It's kind of missing out on a lot of the sort of noise over here. And as I mentioned, you get crazy stuff on the boundaries. This is an artifact of, right, polynomials. So if we think about the error, right, which is the distance between our points and our line, you can see that the polynomial function does a way better job than the linear regression, right? The points are going to be much farther when I have a line that goes like this. But I do have some weird things happening over here, and it's definitely not always sort of matching with our true function. Okay. And although the polynomial function introduces a lot of sort of flexibility, you oftentimes end up with this sort of thing happening. Okay, any questions so far? Sure, we can take a look at that. Okay, so we're going to plot the residuals. This is going to be our polynomial model dot 25 and residuals for the polynomial model 25. Yeah, a lot better, much better. We do want it centered around 0, and that funky stuff that's happening at the beginning, clearly there's some bias, right? There's not as many points down here as up here. So you can kind of see that in the residuals, but generally it's not bad. Okay. But can we do better? So the next thing that we look at is the piecewise or segmented regression. So here we're actually going to need a library called segmented. Oh, what did I do? What the heck? Okay. So you guys will need to install this package. But this is a library that will allow us to run a function called segmented, which will perform a series of linear regressions. So let me pull up this so we can see what everything is doing. Oop. Here we go. No results found. Uh-oh. Huh. Maybe their documentation is not so good. All right. So seg.z is essentially the axis of points that we want to put our breakpoints in. And then psi are the range of locations essentially that we're feeding into the piecewise model for it to think about where to add the breaks. So we will run that alongside a prediction. Once we have that model, so that we can plot the fit. Oops, didn't load the library. Okay, from equals 0.5. You'll note that it took a little bit longer here to run because, because it has to find the breakpoints. Okay, what did I do wrong here? Sequence. Formal argument by match by multiple arguments. Oh, oops. That has to be 2, not by. Sorry about that. So we'll try that again. All right. So I'm going to plot. Oh, not that. I'm going to copy and paste this thing again. Same plot as before, and except now we're going to add our piecewise linear regression. And let's see what that looks like. Okay. So you can see these are very close to my true line. We know that unlike in the polynomial part, we don't have some crazy stuff happening over here. And even here, we're getting some of the nuance of this smaller sort of wave here, and the amplitudes match very closely. So it's doing a pretty good job, except it's got to make some pretty sharp turns, right? You can imagine that any places where you have sudden changes in the slope, in order to represent that in a smooth way, you'd have to have like many sort of breakpoints sort of lined up right here, right? Because you'd have a line like this, like this, like this, like this, like this. And so that's one of the drawbacks of the piecewise linear is you're going to have these kind of kinks in your lines. So what do you guys like better, the polynomial or the piecewise? Piecewise? Okay. Sorry, what was that? The segmented? So this is the function that we use to fit the line. This is like LM, but for polynomial, or sorry, not for piecewise. So you feed in the linear model that you've already done, and then it's going to take that and then break it out into multiple segments. Yeah. So seg.z tells you what set of data to put the breakpoints on, like on what axis. And then psi is the range of x's across which you're considering where to put the breakpoints. Yeah, so it will help you decide the breakpoints. But I think you have to give it an initial set of breakpoints, which is what the psi is doing. Yes. We don't. Yeah. Yeah. Well, okay. I take that back. So the segmented function has a little bit of stuff inside of it that will help try to not overfit. But it is partly having to do with this psi thing. And if you put too many in there, it is possible it is technically possible to overfit, although the function should be able to handle any sort of reasonable set of breakpoint possibilities that you give it. Yeah. So no. So okay. Essentially what happens is that list, psi equals list, you're saying, okay, here are the places that I would like for you to consider a breakpoint. And so I've given it like these increments all the way across the range of x's. And it says, okay, I'm going to take this list and I'm going to do some internal stuff to figure out which of those breakpoints that you gave me that I'm going to select to put ultimately into my regression. Okay. We're kind of glossing over some of the nuances of this function because people don't really use this. Okay, we're going to mainly focus on thinking about the splines. And so let's go ahead and build that out. So the next step of things that I want to do is to look at a cubic linear. So that would be something like this. And then I want to segment it. So cubic segmented dot model. And I'm just going to have one breakpoint right in the middle. And let's see what this looks like. I'll have to do a little finagling to get the predicted values. But don't worry too much about that. Let's just see what these results look like. Okay, so what I've done is I have created a cubic linear model with a polynomial terms going up to the cube. And then I put it into a segmented regression with a single breakpoint at 2.5. And then I've generated the predictions for that so that I can plot it. And that looks something like this. So the function actually ended up moving my breakpoint, which yeah, is one of the features of it. It tries to think about sort of a better location for the breakpoint. And you can see it's not sort of continuous here. So this is the type of thing that we're going to really focus on when we think about splines, except that, you know, our breakpoint here is going to become a knot. It has those extra constraints to make it smooth. And then it's all about how many knots that you have in here that's going to allow it to kind of fit to this closer function. So this is essentially what's going to be happening behind the scenes for what we're doing in the next part, except you've got the extra addition of those constraints that make it smooth. So this is our continuous piecewise cubic function. And we could, actually, I kind of want to see, let's see what happens if I do make it with the same set of breakpoints that I had in the other one. Actually, I haven't done this before, so we'll see what happens. So because it's not, because we don't have the constraints for smoothing, you still have sharp kinks, although they might be slightly smoother. And then the curve of it is probably fitting a little bit closer to the blue in some cases. And you see some stuff like this happening, which may or may not be more or less accurate than the segmented linear. All right, so the last one we'll look at is the cubic spline. So we need to download another package called Splines that will let us do spline stuff. So here we're going to fit into LM, Y regressed on, and then I have a function here, BS, which stands for basis. And the basis function is the thing that transforms my x's into the things that I need for my cubic splines. So I'm going to have x as my input, and then I'm going to have knots. And the knots are going to be specified by location here. So one of the nice things about splines is that you have flexibility both in the way it shapes the polynomial, and you have flexibility in the location of the knots, and you have flexibility with the number of knots. So before, when we think about the location of a breakpoint in a segmented regression, right? You guys were asking, well, how do I know where to put them? How many do I need? Here, it's kind of less important because the location that I put a specific knot, if I put it in, let's say, quote unquote, like the wrong place, a lot of that error can be made up in the polynomial function shape. Okay, so if I put a knot here versus here versus here, that's just going to change the polynomial shape to accommodate that. So you have a lot of flexibility here in being able to decide the location of the knot. So I'm going to, what did I do? Oh, thank you. Cubic. Okay, actually, I'm going to take it out of here. So I'm actually going to copy and paste this a couple times. And what I'm going to do is modify the number of knots each time. So I'm going to increase the intervals here. So I'm going to go 0.5. So there's going to be twice as many knots there. I'm going to have 3 cubic spline 3. And we're going to go by 0.3. So there's going to be about 3 times as many knots in that one. And then lastly, we'll do for cubic spline 4. We'll go by 0.1. So there will be 10 times as many knots. And let's see what happens. So we'll make our plot, X, Y, color gray. Put in my X values. And then I'm going to add all of my lines, and I'll make them different colors. Do that red. For number 3, we'll have this be orange. And then for number 4, we'll have this be forest green. All right. Oh no, I need to run the regressions. Oh, wait, what happened? I'm going too fast here. All right, that works. Predict. That's fine. All right, cubic dot predict 1. I guess I don't need, oh, because I didn't, okay, sorry. You don't need this dollar fit. Okay, so what is our order? Blue, red, orange, green. Okay, so blue here, that's 5 knots, I think in intervals of 1. Looks actually pretty similar to a straight line. Okay, and as you add more and more knots, so red, we're starting to see some closer fit here. And then once we get to orange and green, we're starting to get sort of much closer. So let's look at these one at a time. Let me add in my original curve. And let's just look at the orange and then the green. Oops, not here. Okay, so let's look at cubic predict 3. How this does. So we can see it's offset a little bit. It kind of has a harder time here because it's not given as many knots to work with. But generally the shape of it looks pretty close. And then let's take a look at adding the last one. So you can see the green line here is almost completely overlapping with the blue. It's even getting this part here pretty good. There's a little bit sort of offset here, right? But this is capturing this. It's been doing this better than any of the other models that we've seen, and kind of lines up perfectly with the blue. Okay. So you can see the power, hopefully, of this kind of spline approach in that it's really closely able to replicate very complex functions as long as you give it enough sort of flexibility to work with. You can look at the betas for this, right? But it's betas for this weird transformed cubic continuous function. So they're not really interpretable. So I can no longer kind of describe to you in a really interpretable way the relationship between the x and the y's, right? But I can do a really good job at predicting the sort of right outcome. And so depending on what you want to do, right, we're starting to stray a lot more into, again, the sort of prediction territory rather than interpretability territory. Let's have a look for fun at adding way too many knots. Knots equals sequence 0.5 by 0.0025. And let's see what happens. Oh, no. Okay, so this interval will have what, 40 times more knots than the one than our final one. So 400 times more than the original. Overfit anyone? Yeah, so these lines are going like this. It's passing through all the points. So you're gonna have like an error of 0 unless you have a out of sample prediction, in which case you'll probably do really bad. Can you imagine if I had a point in this white space over here, the error would be this up to wherever the heck that line is.
Why do you leave out points of band?
Oh, that was probably my location of knots, something like that. Not sure. No, I go to 5. I don't know, to be honest. Yeah. Oh, actually, I do know. Yes, this is the next thing that we were going to talk about. So the ends still the ends of my cubic functions actually still have they'll actually have these larger standard errors, and they could do some funky things because you still have these polynomial functions that might act kind of strangely at the boundaries, which might be partly why this is happening. So there's a way that they deal with this. So natural splines. So splines can have high variance in outer range of predictors. Natural splines add constraints So that function is linear at boundaries. So with a cubic spline, it might look something like this. Whereas with, actually, let me just draw it with a different color. With a natural spline, you may have tighter errors at the borders. And with a natural spline, we can look at this as well. Oop, I didn't stop sharing my screen for this part. All right, hang on. Okay, yeah, so this is what, for everyone who's not here and watching the video, this is what I was just talking about here. Okay, we'll jump back over to the code. So similar to our cubic splines, natural splines is what NS stands for instead of BS for the basis function. This knows that it's going to be cubic. With 10 degrees of freedom. Putting in my prediction. And let's look at this a couple times. And I'm going to add in, oh, do I have some kind of error here? Yeah, I do. By 0.01. So here, I'm going to increase the degrees of freedom, which basically means you're going to have more knots. Oops. We'll have 15 and 30 degrees of freedom, like so. Okay. Uh-oh. I have 2 decimal points. Oh, I do. Yes, thank you. Okay, and I'm just going to copy and paste my plotting code, which you guys can reference later if you want. This just includes the standard error terms. And you guys can go back on your own if you want to look at the standard errors for our cubic splines versus our natural splines, and you should see that on the boundaries it gets quite a bit larger. This is kind of hard to see, right? So let me do these one at a time. I'm gonna skip the first one. We'll look at our second fit. Oops, let me pull that up. Okay. Here we can see with 15 degrees of freedom, kind of what this looks like. Not that great of a fit. So let's add some more degrees of freedom. Skip on down to here. Okay, and here looks like it's doing a pretty decent job and probably going to look very similar to our true value. And then here we have smaller standard errors than you would see in the cubic spline. Okay. Any questions about this so far? Yeah.
This is a subset of the it's just a cubic spline with these constraints. But it
Yes.
still has breakpoints and not.
Yes, exactly. That's what the degrees of freedom are for. Yes. You wouldn't. You would usually, yeah. This is kind of like, we're building up, from segments and polynomial, combining that into natural splines as the sort of second end step. Okay, so natural splines actually are pretty common. People use these pretty often for certain applications. There is one alternative, which I will talk about now. Let me stop sharing this time. Yes.
So in this case, like we're using degrees of freedom or not, but it still takes into account the number, right? So when you're looking at the segmented library, it was not like it was choosing the number of breakpoints. That even though it gives more breakpoints, it will choose the number of breakpoints. But in Splines, it like follows whatever the total number we put in.
Yes. Yeah, exactly. And then it'll figure out the locations for you.
Right. But you don't really optimize on the number of breakpoints or degrees of freedom.
No, the degrees of freedom are what you feed it. So the difference, right, is that in this case, in the segmented one, you feed it candidate locations of knots and it chooses from those. Here, you give it the total number of knots and then it chooses the best locations. So they're both doing some stuff behind the scenes to kind of help figure out, yeah, the sort of how to mess with those parameters that function is allowed to work with.
But the number of knots or breakpoints, that number will keep constant. It will still follow whatever the user has inputted, right?
Kind of, yeah. For the segmented one, it's selecting among a candidate set, but it doesn't have to choose all of them. But for this one, you're giving it a number and it uses that many. Yeah. Okay. Last thing we'll talk about are smoothing splines. So in a regression, we're minimizing the RSS. So the residual sum of squares. And what this looks like in a spline is something like this: yi minus g of xi squared, or b, I think I had that earlier. But this is basically our transformation function for our x's. So where g xi is the spline cubic function that constrains the first and second derivatives to be continuous. Okay. So suppose we have a knot at every single point, then we could legitimately have an RSS of 0, right? By doing something like this. But there are actually sort of many ways that you can sort of manipulate this function, the polynomial portion of it, to still have an RSS of 0, right? I could even go like really, really crazy. So all of these things will perfectly minimize the RSS, but we can imagine that compared to the first line that I drew, maybe all these other guys have some kind of overfitting. So how can I deal with that? So let's shrink the second derivative. Okay. Does this look somewhat familiar at all to you guys? Yeah, ridge regression, exactly. So this is the analog for kind of a ridge regression in the context of doing splines. So like a ridge regression, this penalizes the function by encouraging smoothness. So the rate of change of slope should not be big. So if I have a plot here, with a low sigma, that means my tuning parameter is really small. The penalty for having sort of big changes in slopes is smaller. And so I might have some function like this. Versus a high sigma. Which might look something like this. because it's penalizing this line's ability to go up and down, essentially. So with this smooth spline, it is now you don't even have to give it any information about the number of knots. It has one knot at every single point. And then the thing that it's working with here is this tuning parameter that allows for the smoothness of this curve to be very smooth or sort of very up and down, disjointed. I don't know what the word for that is. All right, how do I choose my lambda? Hey, there you go. Cross-validation, right? I can use out-of-sample cross-validation to select the one that gives the best out-of-sample fit, yada, yada. You guys know the spiel here. Okay, so let's finish out today looking at this in R very quickly. Okay, so I'm just going to copy and paste this because we are running low on time. There is a function called smooth.spline. And our spar, oh my gosh, I didn't. All right, display on, screen down. I'm getting way ahead of myself here. Okay, so smooth.spline is the function that lets us do these smoothing splines. And then sbar is our parameter for lambda. So sbar equals 1, super smooth, all the way to sbar equals 0, lets it do kind of whatever it wants. Okay, and we're going to plot all of these guys directly. All right, so here's our points. Here's the first one that didn't work. SP model 1 not found. Didn't I just do that? Okay. Okay, here we go. I don't know what happened there. There is our first guy. You can see that with lambda equals 1, extremely high penalty on the line's ability to go up and down. So it's almost like a straight line. Here is with a lambda of 0.75, we can see that it's allowed to be a little bit more squiggly. Green, even more so. Orange and black. Let's look at this a little bit more carefully here. You can see that it is starting to be a little bit more squiggly. So this is probably overfitting, right? similar. Let me see, is that happening at all with orange? A little bit with orange as well. We're starting to see how it kind of strays a little bit. So the nice thing about this is that it will do the cross-validation for you. Instead of specifying the value that I want for my lambda, I just say cross-validation equals true, and it will do all of that internal out-of-sampling validation automatically. And it will do this. So let's plot this guy. So what I have here is a spline whose lambda was chosen using a cross-validation procedure. And then comparing, so our red is the true function, which we use to create these points, and the blue is the smooth spline. Yeah, that's right. So you can see how the red compares to our blue here. And you can see it's almost a perfect match. Okay. So we've today kind of step by step built our way up to, I would say, the sort of most common sort of spline function approach to doing these fits to these highly nonlinear problems. Okay, so this is a sort of nice technique that allows us to be able to fit very complex nonlinear functions with, right, a very simple set of parameters having to do with just in the earlier splines, right, the knots, and then in this case, just with this single lambda parameter, we can get, right, with a single parameter, I can get a line like that. It's very impressive. And we'll start to talk about some sort of practical applications of this type of thing in like real data sets next time. Okay, any questions? All right, if not, I will see you guys on Thursday.